the history of galaxy classification, you probably know very well the 20th century and the 21st century goals. But we can start from the 18th century, in fact, with Thomas Wright. He made a book. It's an original theory of new hypothesis of the universe in 1750. And he explained that the appearance of the Milky Way was an optical effect due to the immersion, our immersion in what locally approximates a flat layer of stars. He also wrote that some nebula that we can see may be external creations, what the later Kant called island universes. Also, the work of William Herschel between the 18th and the 19th century published a catalog of nebulae in 1902 with 2,500 objects, and it extended the catalog in 1820 up to 5,000 objects, and many of them were galaxies. And well, also the work of the William Parsons, the early of Rose, who built an enormous telescope for that time of 1.80 meters, and he discovered the special spiral nature of the M51 galaxy, the Whirlpool galaxy. Then we have what you probably know better, which is the Shapley-Curtis divide, the Hubble classification, and its mentioned lately, the Baculars classification, the appearance of the radio astronomy. In the 60s up to the end of the century, started infrared observation, simulations, Hubble, Sloan, and so on. And now we are in the time of the Spitzer survey and the machine learning, dark universe, and ALMA and James Webb telescope. Well, what's the challenges in the traditional classification? The first one is the subjectivity, it's the Hohmann bias. But the other one is the time-consuming. It's you cannot escalate the traditional classification for the forthcoming catalogs. And so the automatic morphology classification of galaxies has been studied by several authors. I cannot include all of them here, but just to have an idea. Starting from the Strateva et al. In 2001 classification, they separated the late type galaxies from the early type galaxies using this U-R plane. And then also some classifications using either photometry and geometric parameters, using, for example, spectral energy distribution templates, automatic determination of morphological parameters and classification, but some other authors, subvector vector machines, and particularly the Gaussian VM code, random forests, and neural networks. Most of the classifications have been done using images, and it's particularly interesting in the last years. This transfer learning ImageNet. ImageNet is a large database of images. They are not astronomical images, they are usual objects images. But the neural network trained with ImageNet, you can retrain it. A methodology that is transfer learning, and you can use it for other tasks which was not trained for. So we have these works, but they are also like most of the works based on images. And there are a few works using a spectra. Portillo et al. Use a spectra and neural networks for classification. In this work, we will use this presentation. I will show you how we did this spectral classification, also using neural networks. For that, we used two databases, the Galaxies Zoo2, because it has the classification of galaxies made by observers, and the Sloan digital sky survey that we can get the spectra from Galaxy Zoo from the Sloan digital sky survey. Well, here the preparation of data was the first thing was to select the galaxies, 2,000 galaxies from Galaxy Zoo. We got the spectra from the Sloan, and we tried to use a balanced data set of early type and late type galaxies. Here you have the distribution. In green, there are the late type galaxies, and in orange are the early type galaxies. The second thing was data cleaning. The data was very incomplete. Not all the wavelengths were represented in all the spectra, so we have to put and throw away some of the spectra. And finally, when we have a balanced data set of galaxies and were covered in the spectral range, we made a resampling because there were too many data in the spectra, and a normalization of the spectra. And here I present which is the model architecture of our methodology. We here have the input, which is the spectra. And we have first an encoder chunk. This encoder chunk is consisted in an encoder layer with 1024 nodes. And then we use two Gaussian distributions to explain the this encoded layer. I made a sampling of these distributions. During training of the neural network, training was basically to make this an autoencoder. We need the decoder chunk, which is similar to the encoder layer, and we get the output of the spectrum. Once the model was trained, we could hear, and the output of the encoder chunk we pass to. It's a two-dimensional distribution. We pass to the classification chunk. which is not a neural network, it's a Gaussian Mixture Model. And this shows which is encoded the spectra cluster, makes clusters of this output. Well, more or less the variational autoencoder that we are using works with minimization of the differences, the quadratic differences, sorry, and the Kullback-Leibler divergence, which is a measure of the difference between the two probability distributions. When they are Gaussian, it's a little simple. And the reparameterization trick, which is introduced basically to make the sampling operations differentiable. And so we can see the architecture of the typical autoencoder, variational autoencoder, which is the data input, the data output, which should be the same or very similar, the encoder, the distributions. We use two, but maybe many others. For example, Portillo et al. Use 6. Here, this is the sampling of the parameterization trick, and here is the sampling of the distribution. And then we have the decoder, and we get basically the same input that as output. For making the best dimensionality reduction, we use the Kaike information criterion and the Bayesian information criterion, and with these dimensions. And we see that for one dimension we have a very good result. The information criteria, when you need that it's the lower, when the lower the better. And so for the Kaike, the one dimension was enough. For the Bayesian, says, well, one dimension, but maybe it's better 2 or even 3. We made some probes, and yes, sometimes the one single dimension was enough, but usually 2 dimensions gave all the things that we need. And of course, if you use more dimensions, then you get more fitted spectra. And the kind of spectra we got after autoencoding is this. In red, you see the one of the spectra, raw spectra, and in blue is the reproduction made by the autoencoder. As you see, it's some kind of filtering, and it absolutely erases any trace of emission lines or absorption lines. But it provides a visualization of the continuum. Then, when we get this spectra by the autoencoder, we had, let's say, 2 distributions, and we pass to the Gaussian mixture models. Basically, the Gaussian mixture models fits several Gaussian distributions of unknown parameters. No? For example, if we have this data here, this green data, and we use one single Gaussian, we get something like that, but 2 Gaussians provides a better description. The important thing is that each mixture component represents a cluster. And the data is classified by the probability that it belongs to one or to the other cluster. So what we got as an encoded spectrum? Well, when we use the autoencoder, when we use the encoder chunk, we got this data. Not in colors, we got this in, let's say, in gray. We don't know which are the early type or late type galaxies. But as we use a database that we already know, then we can put the colors. No? And we see that the late type galaxies distribute on this straight line, and early type galaxies distribute on this arc. And this is consistently, then from after fitting the data several times with the autoencoder, we got most of the times this representation. Sometimes we get a distribution that is a straight line, and then all the data, all the early type galaxies here in this point, let's say. And these are the cases that one single dimension is enough to explain the data. No? But most of the times, 2 dimensions are needed, and it's okay. Then we have here the original data, and we have here the Gaussian mixture fitting. As we see, all these all of these few points that are here, that are early type galaxies, here disappear, and some of the late type galaxies disappear here. This is for the training data set. For the test data set, which is much less galaxies, but we got more or less the same shape. These are the actual early type or late type galaxies, and this is the classification of the Gaussian Mixture Model. Well, we made several bootstrap statistics, several runs of the models to get bootstrap statistics, and we find that using different thresholds for the classification, with the default, it's about 85% the accuracy. Optimize it, putting a threshold, choose with more attention, that's 0.5, we get a 0.80 and 86% accuracy. And here I show you the area under the curve or bootstrap statistics. It's we see that most of the area under the curve is between 91% and 93%. So it means that we have a good classification. And I think that I have finished it now. It's been less time that I thought I will need, but the conclusions of this work is our objective was artificial intelligence galaxy morphology for classification using spectral data. And we we have got results using a variational autoencoder and Gaussian mixture models, and it shows that it's a promising methodology for this classification, because you have to take into account that it's unsupervised. So we can do, in principle, although we use the known classification, but the model was not using that. I mean, here, this classification was generated without knowing the levels of these galaxies. And well, this is part of the larger work that we want to apply this to the Lockman Espresso project, the spectrum of galaxies. And we want to integrate this, the Hubble Space Telescope images for labeling these galaxies of the Lockman Espresso. The field of the Hubble is about 30% of the Lockman Espresso field. So most of the galaxies, we don't have accurate images, high resolution images for classification. So we want to train or transfer learning our training with the Hubble and with the Sloan galaxies to classify the rest of the Lockman Espresso galaxy fields, below galaxies. And the research impact of this is basically it may be a significant contribution during this new epoch of big astronomical data. And well, you have here some references of this work, and I want to finish with an acknowledgement to the dedicated staff at the IAC, to the Professor Jordi Sepa and all his team, who are very encouraging for this work, and the Fundación Jesús Serra, which provide a grant for me to be in the IAC during the summer. Thank you. I've already finished.
Okay, I think I was mute. Okay, now you can hear me. I just thank you for the talk, Antonio. I just want to say that I want to apologize that I could have some technical problems at the beginning, so I could not introduce you and the seminar properly. So I'm sorry for that. My computer froze and I could not do anything. And so if anyone has questions, please raise your hand, and then I can just you can just unmute yourself and ask them, or just write it in the chat.
There are no questions in the chat already.
I don't see any. Okay, if there's any, I think we can finish the seminar.
Okay.
And thank you again, José Antonio,
You're
for the
welcome.
talk.
Thank you. Bye.
Yeah. Bye bye.
Thank you.
Thank you.